Hello everyone, myself Teja Vikram. Today I am going to explain about a topic in control systems called homogeneous and non-homogeneous equations. So let's go into the topic. Linear differential equations in control systems. This presentation introduces linear differential equations, a cornerstone of control systems engineering. We will explore the distinction between homogeneous and non-homogeneous equations, highlighting their roles in modeling dynamic system behavior. Understanding these equations is crucial for analyzing and designing control systems that govern various engineering applications. We will discuss fundamental concepts, solution methodologies, and practical applications, providing a comprehensive overview for both students and practicing engineers, from stability analysis to real-world examples. This presentation aims to bridge the gap between theory and practice, offering valuable insights into the field of control system. Homogeneous equations. Homogeneous differential equations are defined by having a zero right hand side. Their general form is expressed as dx by dt into p of tx is equals to 0, where the equation equals 0, indicating no external forcing function. These equations exhibit unique solution structures characterized by linearity and the superposition principle. So uh, now see the derivation of homogeneous linear time invariant system. So let us consider a state equation, that is x dash of t is equals to a into x of t plus b into u of t, where the u of t is equals to 0. As we said, the right side of the equation is 0. X dash of t is equals to a into x of t. If a is constant matrix and u of t is a zero vector, the equation above represents a homogeneous linear time invariant system. Coming to derivation, x dash of t is equals to a into x of t. So applying the Laplace transform, it becomes as si into x of s minus x of 0 is equals to a into x of s. si into x of s minus a into x of s is equals to 0. So if here the a into x of s sent to the left side, so it becomes as minus a into x of s, and the minus x of 0 is sent to right side, then it becomes uh, plus x of 0. If we take out the common, x of s is x of s into si minus a is equals to x of 0. Then x of s is equals to si minus a into a inverse into x of 0. So for this equation, we apply the inverse Laplace transform, then it becomes as x of t is equals to phi of t into x naught. So this is the derivation of the homogeneous equation. So coming to non-homogeneous equation, non-homogeneous differential equations include a non-zero functioning non-zero forcing function represented in the general form as dx by dt plus p of t into x is equals to q of t, where q of t is the forcing function. The key difference from homogeneous equation requires different solution methods, such as variation of parameters. So let's see the derivation of non-homogeneous linear time invariant system. So let us consider the state equation as x dash of t is equals to a into x of t plus b into u of t. If a is a constant matrix and u of t is non-zero vector, the above equation represents a non-zero homogeneous linear time invariant system. X dash of t is equals to a into x of t plus b into u of t. So applying the Laplace transform to this equation, it becomes as si into x of x of s minus x of 0, that is equals to a into x of s plus b into u of f, u of s. So now we are taking common x of s, then it becomes as x of s into si minus a is equals to b into u of f, u of s plus x into x of 0. So the si minus a is sent to right side of the equation. Then it becomes as x of s is equals to b into u of t into si minus a inverse plus x of 0 into si minus a inverse. So now we apply the inverse Laplace transform. If we apply the Laplace inverse Laplace transform, it becomes as x of t is equals to L inverse b into u of s into si minus a inverse plus L inverse x of 0 into si minus a inverse. This is the non-homogeneous equation derivation. So let's see some solution techniques for non-homogeneous equation. Solving non-homogeneous equations involves finding both particular and complementary solution components. The superposition principle is applied to combine these solutions, and methods includes analytic and numerical approaches. Handling different forcing function types is essential. Particular solution, solution specific to the forcing function q of t, and a complementary solution to the associate homogeneous equation superposition, combined particular and complementary solution. So these three are the techniques these three are the solution techniques for non-homogeneous equation. So now let's see the stability analysis in control systems. Stability analysis in control systems utilizes stability criteria for homogeneous equations such as the Lyapunov stability theorem. Eigenvalues play a crucial role in determining system stability, and concepts like transition matrix are fundamental. So now we will see some practical applications in engineering. Linear differential equations are fundamental in various engineering applications, including control system design methodologies and modeling of mechanical and electrical systems. State space representation and transfer function analysis rely on these equations. First one is modeling, representing real world system mathematically, and the second one is design, creating control systems to meet performance goals, and the third one is analysis, evaluating system behavior. So these three are the applications of the control systems in engineering. So let's see the conclusion and key takeaways. Linear differential equations are critical in control systems. This presentation connected theoretical concept to practical applications and highlighting both challenges and advanced solution techniques. Future research directions in control systems aims to address these challenges. Key points are: understanding homogeneous and non-homogeneous equations is essential, and the stability analysis relies on eigenvalue analysis and Lyapunov theorems. Practical applications span mechanical, electrical, and control system designing. Third one is, and last one is future directions. Advanced numerical methods for complex systems, adaptive control techniques for non-linear systems, integration of machine learning for system identification. So this is about the derivations and some brief notes on the homogeneous and non-homogeneous equation. Thank you one and all.